Hello everyone, we discuss contest 19 today. I would say pretty normal contest, not as difficult as I expected to be. So last few problems, okay, especially the last problem is kind of tricky, but at least two people solved the problem, and I encourage you to solve it. If you didn't solve it during the contest, solve it later. It's okay. It's not as hard as it looks. Um, yes, and all other problems are also solved. Good for you. Good. I made a lot of mistakes during solving this contest, but that's mostly because I'm not in the best shape today. But overall, I solved the problem. It took like an hour. So let's go. So the first problem is already not very trivial. So sometimes I have I give you the contest when the first problem is very straightforward. You just read the problem statement and immediately get the solution. This problem is a little bit more tricky. So what we need in this problem, we have some array, and we want to make this array a permutation of numbers from 1 to n. And the question is how many numbers you need to change in order to make this array permutation. Idea is very simple, so if you want to change the minimal amount of numbers, then you want to leave the maximal number. It's quite popular idea. So instead of maximizing something, okay, sometimes instead of maximizing you minimize something, or instead of minimizing you maximize something. So here, instead of minimizing number elements I change, I maximize number of elements I do not change. Yeah. So if I do not change numbers, then the numbers I leave must be in the permutation. Which numbers can be in permutation? In permutation, I can have numbers from 1 to n, and I need them all of them to be different. Yeah. So what I'm doing here, I check. So I read this number x, check if it is number from 1 to n. So it's a valid number for permutation, and if it's not used yet, so I check that all numbers I use are different. Then I use this number, mark it as used, and decrease the answer. So my answer will be n minus number of the elements I do not change. All other elements will be changed. Yeah? So it will be n minus number of elements I leave. So that's it. That's basically the whole solution. Not trivial problem, but it's not hard as well. That's it. So that's problem A. Let's go to problem B. Problem B is already, it's even more tricky, I would say. So what we have in problem B, we have, okay, so first you need to understand what's going on in this problem. So you need to build a string of n different letters, and for each letter, you know the maximal number of occurrences of this letter you may have, and you also have this property that all the numbers of these different characters should be distinct. So number of occurrences should be distinct. So you cannot have two numbers with the same number of occurrences. Quite natural greedy solution. So what I will do, I want to make this string as long as possible. So for every number, I want to take it as many times as I can. So let's pick the maximal number of times you can take is this. So this AI is the maximal number of time you can take. But sometimes you have equal numbers. If you have equal numbers, then one of these characters should be less than AIS. So what I'm doing here, I just greedily decrease this value x until it is unique. Yeah. So I read this number x. X is one of this number AI. Yeah? And then I decrease it while it is invalid. It is invalid if it is greater than 0 and it is already occurred in my sequence. So I take number. If I already have this number before, then I decrease it until I have some unique number or 0. Yeah. Okay, kind of natural greedy algorithm. It's easy. It's actually easy to prove. You can try to prove it. Basically, every time we add the new number, we get the optimal sequence. Yeah. So after adding every number, we have an optimal possible sequence of maximal possible sum. So it's kind of okay. It's intuitively correct. If you want to make a formal proof, you can try it. It's good exercise. So that's it. So again, that's the whole solution. Greedy solution. We read number x. So I don't put them in array. So you can put them in array. This array A. I just take them one by one and just greedily decrease it until it is unique. Solution is pretty slow, so it works in n squared time, yeah. So for every number here, I may decrease it here up to n times. But here is n is small, n is up 26, so it doesn't matter. So basically any solution with some small polynomial time will work. So you may, for example, you may just take these numbers, find any pair of equal numbers, and decrease one of them by one. Yeah, it's kind of that's easier to prove of the greedy algorithm. It's very safe step. If you have two equal numbers, then at least one of them should be decreased by at least one. So let's decrease one of them by one and continue. Yeah. Again, find some pair of equal numbers. Again, decrease one of them. Yeah. It's even easier to prove than my solution, but it will work in like n cube time. It will also pass this. Actually, this problem can be solved in linear time, in n log n time. You need to sort these numbers. After sorting, it can be sorted in linear time, but it's not required in this problem. So n is small, so you can make any even not very optimal solution will work. So you just need to get this job done. So this problem is not about effective algorithm, about time complexities. Mostly it's just about getting the problem solved. So that's it. So this is my solution, not very optimal, but optimal enough to solve this problem. So I just thought about the easiest way to solve this problem, and that's my easiest way. I utilized sets in this problem here, you see. It can be solved without any data structures, basically, but we still, if I have sets, why not use them? Okay, here I forgot to insert the element. Okay, so that's it. Okay, here today I learned you can do it like this in modern C++. There's met contains. Yeah. You learn something new every day. So that's it. That's problem B. Now let's move to problem C. Comes about the queue. So okay, problems has a long problem statement. It's kind of less, I would say, less math involved in this problem. So you don't need to. You just need to model what's written in problem statement. So they give you some model, and you just need to simulate it and see what will have as a result. Multiple ways to do it. I did it like this. So again, let's look at the state of my queue. You can do it differently. So you can just analyze, for example, events. So you have event, the student come to the queue, or the student left the queue, or something like this. I did it differently. I just make the initial. I put all the people in the queue in the beginning, in the order they come. Yeah, and then just analyze this queue from left to right. Yeah. So I know in which order the people will be served in the cafeteria. What in the tray. Okay. So I know in which order the people will be served. Yeah, in the same order they appear in the input file. So here I'm trying to sort them by the L, but then I read that it's sorted by L initially. Yeah, so you don't need this sorting. They already sorted. And now I just go in this sorted order and check for every person if we can serve them or not. Yeah. So T is my current time. I take the next person. Skip all the time before this person comes. So if my time is less than L, I move it to L. So now T is the first time I can serve this person. Yes, it's the minimal possible time I can serve this person. I see if the person is still here, so if T is less or equal than R, then I serve him and continue in increase T. If my time is greater than R, then the person left. So I just make result equal to 0 here and just keep this person. That's it. That's okay. So that's the whole solution. Some people, okay, so for some people it was not okay. It's a little bit unnatural how it's written in problem statement. Let me show you. So it's written like this. So it's written that so if at the beginning is not get this T, then it's leave the queue. So it looks like the person is leaving the queue at time Ri already leaving, yeah? So if we can serve him at time Ri, so you need to put greater or equal here, yeah? Because person is leaving at second Ri. But okay, if you read this line carefully, okay, it's not written very good. Sometimes it happens. Sometimes authors write problem statement like this. But if you read it carefully, it's written. It says that if so we live in at second Ri if we are not served. So if we can serve the person in this second, then they will not leave. Okay, so the person leave if we cannot serve them in second Ri. That's what's written here. Yeah. So the person only leaves if the current time is greater than Ri. So if we can serve in the second, we can serve in a second greater than Ri. Then they already leave. And again, it's not covered in the problem examples. So even if you make greater or equal here, you will pass all the example tests and then fail on test something like 4 or something. So a lot of people made this mistake. Happens. You need to be careful. Yeah. Problem D. So for problem D is about carefully checking all the possible cases. So okay, let me stop. Let's stop. Let me show you all the cases. So how do you solve problems like this? You basically play with the model and see what you can do. Okay, so imagine you have some number of elements of R, some number of elements equal G, sometimes of red, what cards, some number of green cards, some number of blue cards. Yeah. So you have some number of cards. And then you just play and think, okay, what can I do? So what color may I have in the end? Okay, for example, what actions you can do? You can replace two equal cards with the same. So basically, you remove one of the cards. Yeah? Or you can take two different cards and replace them with card of the third color. Just two options you have actually. And so let's just play and see what we can do. So if we have something like this, what, for example, we can do? We can remove all R's except one. So we can leave only one card R. We can leave only card G, only one card blue. Now, if we have one card of each type, we can do anything. So we can combine these to have blue cards and then combine these to leave one blue card. Yeah. Or we can start with any other pair. So we can combine these cards to make a red and then finish it. So red. So if we have situation like this, we have one card of each type. Then we can make any card in the end. Yeah. And if you have all three types present in the initial configuration, then you can get any card in the end. Okay, so this is the first observation. So if I have all three types in my array, then the answer is just all three types. That's one of three options actually. So you may have one type, you may have two types, you may have three types. Yeah. If you have three types, then the answer is like this. If you have only one type, that's another easy observation. If you all cards have the same type, then you only can get this type in the end. Yeah, because all your actions create the card of the same type. And finally, we have the final also. If we have some number of red cards, let's say some number of green cards, what can we do? So again, let's play. So let's see what can we do. For example, we can replace all these cards with the single R and all these with single G, and then combine them to get blue card. So this is always an option. Yeah. So we can always do something like this. Yeah. So if you have cards of two different types, you can get one card of the third type in the end. Can we do anything else? No, let's check. No, there is an example for this. So in one of the examples, okay, let me show you. Let me show you. here. So in one of the examples, we show you only have card of two types, red and green, and you can get a red card in the end. See, you always can get blue card, but you also can get red card. And you see this example. Sometimes authors are kind enough to give you a good example. So here you just you just use it. Yeah. So if you have two green cards and one red card, you can get a red card in the end. Okay, how you get red card? No, you need to combine these cards first, and then combine these cards to get red card. And you can do it if you have at least two green cards. Yeah. So again, if I have three types, let's say green and red, if I have at least two green cards, I can make a red card. And vice versa, if I have at least two red cards, I can make a green card. So this is basically all options. So if I have all three types, I can get all three types in the end. If I have only single type, I can get only this type in the end. If I have two types, I always can get the third type. And also sometimes I can get these types if I have at least two cards. So if I have at least two cards, I can make red. If I have at least two red cards, I can make green. Okay, these are all options. So now you just need to carefully implement this. That's also kind of difficult. Okay, you may implement it like this. You may just take look at all possible cases. So problem is that a number of options is kind of high. So you may have only red cards, you may have only blue cards, only green cards. You may have red cards and green cards, or you may have red cards and blue cards, or you may have blue cards and green cards, or you may have all of them. Yeah. So you can make special case for all these. Okay, no, not that many actually, 7 cases. Yeah. So there are 7 possible cases, and you can implement them like this. You just check all these 7 cases. Up to you. It will work. It will work. I tried to make it a little bit more short, so it ended up with some strange solution actually, but you'll see. So how I do it? So first I make array of counters. Instead of just having 3 counters, I make array of counters. Here I actually tried to make a good program. It turns out to be not that good, but you'll see. So here I use these counters to just array of 3 counters. Instead of 3 separate counters, I use array of 3 counters and just increase the counters by character. So I take the character. Stop. Oh, again, I pushed something. Oh, okay. Yes. So I take this string t contains different types of cards I may have. Yeah. So here this line transforms my character to index. Yeah. So I have index 0, 1, or 2, and I increase corresponding counter. See. Here I'm doing something. Okay. See, I will actually rewrite it later. But so here I'm checking which characters actually present in my string. So I look at all counters. If I have at least one card of this type, I add this type to the string D. So string D will contain characters corresponding to all my types. It's actually not better. It's better to have array of integers here and just transform them to characters in the end. But okay, I will rewrite it later. Okay. So what I'm doing here, okay, I check simple cases. So if I have all 3 types, I output all 3 types. If I have only one type, I output only this one type. And then I start thinking, okay. Come on. Oh, yeah. Here I decided to replace my, so actually it's not very good programming. So I replaced my string with the array of integers. So now I have array of types. Okay, replace this. Now if I have only 2 different types, let's put them in 2 variables. So have A as the first type, B is the second. So A and B are the 2 types present in my input. Now the third type can be calculated like this. Yeah. So 3 is the sum of 0, 1, and 2. So I have 3 minus A minus B is the third number. So I have 3 numbers, 0, 1, and 2. Yeah, one of them is A, another one is B, so the third one must be this. So this type C can always be created. Now types A and B can be created if I have at least two cards of this type. Looks okay. Now then I will receive wrong answer. Can you see why I will receive wrong answer? Okay, so if you solve this problem during the contest, you must be clear why I have a wrong answer here. Okay. Codeforce was not very fast today. Okay, so I got the wrong answer. Okay, show me. Yes, wrong answer test 5. So again, I read solution once again. I read the problem statement, read the notes, read solution once again, I believe. Okay, so spent too much time. Okay, it's not my best performance today, I told you. So I just carefully check all the conditions that I'm doing exactly what I plan to do. It looks like it looks like I do it exactly what I plan to do. Yeah. So I'm thinking, okay, what's the problem? What's the problem? Then at some point I decided to read the problem statement once again. Usually it's a good thing to just read the problem statement once again in case you missed something, some small detail. Okay, like this. So in case you missed some small detail, just read all the problem statement once again carefully, every sentence one by one. Because when you read the problem statement several times, sometimes you just skip the details. You think, okay, I know what's happening here, so I'll just quickly uh, read it from corner to corner. It's not how we do it. So if you have wrong answer, just read carefully. Just read all the small details. Maybe you just missed one word. One word may make a big difference. Yeah. So just carefully read it word by word and just check that you didn't miss anything. So I missed the property that I need to output these characters in sorted order. So what I'm doing here, I just instead of doing it from every case, I just put them in this string res and then sort it in the end. So instead of outputting them, I was outputting this directly to the output. Now I just put it in this temporary string res and then in the end sort it. So that's it. That's the whole solution. Yeah. So that's problem D. Let's actually see if you have better solution than I do. Oh, it actually looks better than mine. So f is all true, all equal. If someone not equal, then f is false. Okay, if they're all equal, output this. Makes sense. Now here, oh, that's easy. So you check all possible characters and think if I can get this character in the end, and you can do it if it's not n-1. That's clever. Okay, so if number of this character is not n-1, that's the only case. Okay, that's the only case where that's impossible to get this character if I have n-1 of this character. So I have two types. Okay, makes sense. Nice. So, okay. So usually is actually smarter than mine. Good. So that's it. That's problem D. Let's go to problem E. Okay, problem E is basically about combinatorics. It's simple combinatorics. Basically, you need to find the correct formula, and then that's it. Again, if you're good in combinatorics, and maybe I'm not as fast in combinatorics, so I spend too much time solving it. Actually, it's kind of embarrassing. The idea is kind of easy. So first I read the problem wrong. Okay, so what's the correct approach to solve problem like this? So I have some k element. Let's say you have k elements, and you want to put them in n buckets. Yeah, so you have n buckets, let's say. So you have n buckets and some k elements. So let's have 3 elements and 2 buckets. No, let's have let's 4 buckets. So let's have 3 elements and 4 buckets. And you want to put these 3 elements into these 4 buckets and check how many options do you have. The way you do it is actually like this. And it's possible to put several elements in the same bucket. So again, let's say you have 3. So let's say you have these 4 buckets, and you put some, let's say, 2 elements here, 1 element here. The way you calculate it is like, imagine you have like borders between these buckets. You have one border. Yeah. So if I have 4 buckets, I need to put 3 borders between buckets. And now my situation is like this. I have 2 elements, then separator, then another element, then another separator. Yeah. So your configuration is encoded as a sequence of elements and separators. Yeah. And I have k elements. Wait, k. You have k elements and n-1 separators. So the number of ways you can do it is in Russian notation it's written like this. So it's number of ways to choose k elements out of k plus n-1. Okay, or we do it like this. In Western notation, you write it like this. Yeah. So it's just binomial coefficient. And the way you calculate binomial coefficient, okay, in this problem you can do it anyhow. Again, let me what's the problem? I do it just calculating factorials. Maybe not the best choice. Yes, they called number of visits. It's called the same, but just notation is different. Yeah, you see, they write it like this. Yeah. Again, if you see in literature, that's the same binomial coefficient as this, depending on which literature you read. Okay, I spent too much time because I have integer overflows. It's kind of embarrassing. So let me skip this part. No, I have integer overflow because I calculate these factorials, and I have this n-1, and factorial of n-1 is just too high. Okay. Yeah, so finally I fixed it just by putting k here. So I have so the number of choices is number of choices from n plus k minus 1 of k. So I need, again, you need to put k elements. You have this number of k elements plus separators. And this is just calculate binomial coefficient using factorials. Why I decided to use it like this, I don't know. I thought because k was small, so I thought k is small, so it's 3 or 5. So it's better to do it like this. And maybe for this problem, it would be much easier to do it in Python, I would think. So you don't have any integer overflow problems with Python, so it doesn't matter what you do in this problem. You still can solve it correctly from the first try. But that's this problem in just problem of finding the good formula basically and implementing it. Do we have many submissions in Python? Let's see, status for problem E. I would expect. Oh no, it's actually not that many. So okay. So even with problem like this, you use C++. Interesting. I'm using C++ because it's for educational purposes only. In the real context, I would definitely write this problem in Python, because I feel like I may have some integer overflow problems, and the efficiency is not a problem here. So this problem is not about efficient programming. Yeah. So the Python solution will work and will definitely not have any integer overflow problems. Just my advice for you, if you're doing something like this, just think about doing it in Python. Okay. I usually don't advertise for Python because Python is actually not that good for competitive programming, I think, but especially but sometimes for problems like this, it's okay. Or Java. In Java you have big integers also, nice. Okay, but that's for Java fans. Problem F. Okay, problem F involves some. I was thinking about if I need to if I want to give this problem in the contest or not, because it involves something about probability theory. Yeah, not very high school topic, but again, it's here is kind of simple probability theory, I would say. So what we have, we every day, so we have some number of dresses. Every time we extend it twice, and then with probability 50%, we remove one of them. And we look at the expected number of dresses. Yeah. Okay, you have link. Okay, it's interesting. We have link here. Let me see what is linked to. No, okay. Do they really expect you to read this Wikipedia article during the contest? Yeah. I don't know why this problem is about. So you can easily reformulate the same problem without any probability theory. So basically, what's happening every time? So we have a number. Every day, we we double it and then subtract 1/2. Yeah. So we subtract 1/2 one dress with probability 50%. It's effectively the same as just subtracting 1/2. So we just subtract half of the dress. Subtract every day. So what I'm doing here, I'm just writing the. Again, I'm doing it very often. So I just write the sequence and then guess the formula. Yeah. Again, you can do the same just by writing a lot of formula and then getting the correct one. For me, it's sometimes easier. It's just I just spend less time doing this when I just write the sequence and then guess the formula. So I know the formula should be some exponent. Yeah. So I'm just not sure which one. So I just write the sequence and see which exponent I need to use. Uh, so I write the first like 4 elements and that's enough. Yeah, you see, I already see the pattern. You see, so again, I start from number x. In the next day, I will have 2x minus half. Yeah, then I will multiply this by 2. So I have 4x minus 1 minus 1/2. 4x minus 3 halves. And then I multiply this by 2. So I have 8x minus, here I have 6 minus 1. So I have 7. So I have 8x minus 7 over 2. Yeah, see? So now you clearly see the pattern, yes? So every day your formula here is some power of 2 multiplied by x, yeah, minus, and here, you have some power of 2 minus 1. Yes, well, here's the sequence like 0, 1, 3, 7. It's power of 2 minus 1. Okay, if it's not clear, you can continue the sequence and write some more characters. I just know that the formula should be something exponent, some exponent of 2. It kind of makes sense. So if you double everything every day, you double everything, you should have some exponent base 2, basically. Yeah, you just need to find all the details, and I do it like this. And that's it. Okay, now. Not sure what I'm doing here. Just spend some time. Yeah. So that's it. So I just write this formula. It's basically for educational purposes. Again, usually I will just program it. So this is the formula we need to calculate, and it's easy to calculate. You just include power of 2, and that's it. The problem is that numbers are kind of high here, up to 10 power 18. So you need to use binary exponentiation to calculate 2 in power of k. But that's it. It's easy. Yeah, here I also check the examples that I understand everything correctly. Just check my formula for the examples. That's it. So now I just write here. Here I write the binary exponentiation. Again, normally I would just copy this code from my library. I will not program it from scratch, but here I'm doing it just again for educational purposes, basically. and I encourage you to have library code for this. Yeah, so that's a lot of time you need to write binary exploitation in Codeforce contest. Just keep it ready, just in some safe place, so you can take it and immediately use. Do not write it from scratch, like I did. Why don't do it recursively? It's slightly faster. Do it recursively. Recursion is a little bit slower, so I just used to do it like this. It's not a big problem in this problem. In this problem, it's not a big deal because you need to calculate it basically once. In some another problem, when you need to calculate it multiple times, like when you calculate it million times, it may make difference. Okay, for million, not a problem. For like, if you calculate 100 million times, it may be different. So you can okay, we can make a okay, not today. So make an experiment. Just write it in iterative style and in recursive style. Check which one is actually faster. I expect iterative style will be faster significantly. I would check later and tell you the result. I don't want to spend time now, but yes. So it's slightly faster. That's why I always do it like this, and it's easy to program actually. So this is the whole code. Sometimes uh, the recursive algorithm is just easier to implement and easier to understand. For binary exploitation, it doesn't make sense. It just this is the whole algorithm. So recursive implementation is not easier. So you don't win anything. Okay, and here again I have wrong answer. Yeah, because I forgot the case. Okay, I'm not sure which case, so I read again. I read the problem statement again and find some tricky spots. Yes, find some tricky spots. And here I see the 0 and immediately think, okay, what will happen if I have 0? And I see what will. So I'm kind of removing elements when I have 0 elements. Okay, so here I find this in the problem statement. Okay, think what will happen if you have 0. You need to output 0 because you cannot remove any elements if you have none. That's it. So that was the mistake. I make a lot of mistakes today, but again, happens. So that's it. That's problem F. So it's math problem, I would say, but it's not a hard math problem. Yeah. So just write all the formulas. See what you need to calculate. You need to calculate some exponents. So you implement simple algorithm for calculating exponents in log n time, and that's it. That's the whole solution. Let's move to problem G. Problem G is actually nice. So it is approachable, but I like this problem because it is kind of in. So some problems looks kind of artificial. So this problem looks less artificial. That's something you can actually face in some computer games. So you have some parameters. You have something. You have some process which looks kind of natural. So you deal the damage by some formula. They deal by some formula, and you have some small numbers here. Again, let's stop here. So all the numbers are kind of small, but still you need to solve problems somehow. Yeah. Uh, Again, the key observation in this problem that all the numbers are small. So here, again, constraints are a very important part of the problem statement. You need to solve the problem specifically for this for the data limited by these constraints. So you look at this constraint, the numbers are small, and you think, okay, if numbers are small in integer, maybe I can just brute force some cases. And you think, okay, what can I brute force? For example, you can get some more attack points. Yep. It doesn't make sense to get too many attack points. Yep. Because your monster has some defense. Yep. Yep. So and some health points. Yeah. And if you have enough attack you will just kill the monster in a single shot. Yep. So it will happen if you have, for example, at least 200 points. Yeah. So his defense is at most 100. So you will deal at least 100 damage. And the monster has at most 100 HP. So if you have at least 200 attack points, you will kill him in one shot. It doesn't make sense to have more than 200 attack points. That's a good observation, yeah? So number of attack points should be greater than 200. So it's kind of small, yeah? Next about defense. Same about defense. It doesn't make sense to make more than 100 defense points. Okay? If your defense is more than his attack points, then the monster will not deal you any damage. Yeah? So your defense point should be greater than 100. It doesn't make sense to buy more defense point than 100. Okay, so we limit the maximal number of I can buy attack point number of attack points I can buy, number of defense points I can buy, and now the only deal is HP. Yeah. So how many HP points do you need? Well, it's actually may need a lot of HP points. So it's hard to track them, but you can actually calculate how many HP points do you need. So if you fixed how much you spend on attack points and defense points, then you know how many rounds you need to kill the monster. So you just need enough HP to survive this number of rounds. Yeah? So I will brute force two parameters and calculate the third parameter. That's it. I'll be short. That's too long. Yeah. So that's it. So here I'm just making two loops. So I find my final attack and my final defense points. Yeah. So it should be at least this and at most this. So here I spent like 20,000 iterations. So it's quite low number. Yeah. So I could iterate something else here actually, but I don't need to. I just need to calculate how many HP I need in the beginning to survive this amount. Now I calculate how many rounds I need. Yeah. So you need divide this by this and round it up. You can round up by doing this. So here I divide, and I need to calculate CIL of this number. Yeah. So you do like this. You add this number minus 1. Yeah. So it will be rounded to the closest integer above. Okay, so I calculate number of rounds. Now, you just need to calculate how much HP do you need in the beginning. You see, so how much damage the monster will give me. So if I have, okay, why not? So if I have enough defense, so if the monster is dealing me at least some damage, so if his attack is more than my defense, then I need some. So if the attack of the monster is less than my defense, less or equal, then the monster is dealing no damage. I don't need any extra XP. So my HP is like this. If the monster is dealing me some damage, I need to have enough XP to survive all these T rounds. I'm doing it in strange order, so I'm doing this, and then I will move back and implement this. Not sure why. I just you need to do all these operations in any order. I just do it like in this order. Yep. So this is the amount of which we need. So you need to survive T rounds. Every round your HP is decreased by this value. So you need T multiplied by this plus 1 at least. Oh, that's it. Okay, there is bug in this program. You can find it. Again, examples in this problem are not very good. So yeah. I noticed that the example is not very good, so I decide to double check before I submit, but I didn't find the bug. No, happens. Can you spot the bug? Again, here I get runtime error. When I see runtime error, I immediately think what can cause runtime. There are not that many causes of runtime error. Usually, it's when you get out of the bounds of the array. So you have array, you get out of the bounds of the array, you have something like this. Here I don't have any arrays. So the second cause is division by 0. And I have division. I have actually only one division here. So this runtime error must be division by 0 here. And I think, okay, I forgot that it may happen. Yeah, I actually forgot that I may have just not enough damage. No, no, it's if my attack points are low, I just don't deal any damage. If I don't deal any damage, that's not a good case. I just need to skip it. That's it. That's my mistake. Everything else surprisingly worked from the first try. That's it. That's problem G. Okay, let's move to problem H. Problem H is actually a very nice graph problem. What we have in problem H, we have a tree, and we can compress this tree by applying this operation. So we have these two paths of the same length. We can remove one of them. So we can kind of merge two paths into one. So effectively, we just remove one of the paths. And the question is if it is possible to compress the whole tree into a single path. Here I'm trying to look at the example. So I look at the example, see what's happening in this example. Yeah, I see I can compress these two paths into one. So after that, I have path of size 3. So it does make sense. And then I start thinking. So I'm thinking just by drawing some pictures here. So I think, okay, I compress these two paths, then I compress these paths, I compress these paths, and I immediately see that something interesting happens. That here I compress all the paths, all the leaves of this tree here, you see, they belong to the same level. See? So I have the same distance to all leaves from this kind of middle point. I'm not sure which is with this middle point, but in this I see how this how the problem looks like. Yeah. So I just try and do something and see how the again. So if the answer is positive, if it's possible to compress the whole tree into a single path, I see how the tree should look like. And here I immediately see that I'm doing like this. So if it's possible to compress all these paths into one, then all these leaves should belong to the same level in some sense. Yeah, see? And then I think, okay, if I compress everything here, I can also have the same structure in the top part. Yeah. So here I can have another tree with all the leaves on the same level. Yeah. So this is kind of important picture. So this picture shows me how the tree should look like. Now I just need to formalize it. So by formalizing it, I just need to find what is this middle point. That's the interesting question. So yeah. Uh, so if n is small, you can actually check all possible middle points. But here n is large. So you kind of need to carefully pick this middle point and check on this one. You cannot check this for all possible middle points. At least I don't know how to. Yeah. So I think in how to find this middle point. What is this point? And here I think it looks like the center of the graph in some sense. So I think what it can be. Yeah. And here I see that again, if b is greater than I, imagine that b is greater than I. Then from this point, I have two different branches of size b. See? Yeah. So b is 2b is diameter of my graph. So this point should be at center of my diameter. That's it. That's it. So what I will do? Okay, let me. let me draw a new picture. So what I will do, I will I have this point. I have, let's say I have at least 2 branches here with length b and some branches here of length a. So I have all leaves here at this level, all leaves here at this level. If b is greater than a, yeah. So this is the longest path in my graph, b plus b. Every other path is shorter. Yeah? So your diameter is 2b, and this point is the center of your diameter. Center of diameter is an important point in this graph. It is the point which minimizes the maximal distance to all the nodes. Yeah, there are several important centers of the graph. Like this center. There's also centroid. Sometimes interesting point. Sometimes you have other points. That doesn't matter. So here I just see that this point looks like a center of the graph, like center of the diameter. So I just try to prove if it's true. It's actually true, because this is the diameter, this is the center. Yeah. If you have a single path here, so then this is not longer the center of diameter. Yeah. But if you have only one edge here, you can move this point downwards. You can put this point instead. So you can put this point until you have center of diameter. Center of diameter is always works. That's my point. Yeah. So center of diameter is a good point to start with. Now what I will do, I will look at center of diameter and check that all the leaves can be split in 2 groups. So one with distance b, another with distance a. Yep. Yeah. Actually, it turns out a little bit more difficult. So actually what you need to do, you need to take this center, I put the C. Look at all edges connected to the center, and all these subtrees, yeah, should be split in 2 groups. So some subtrees may contain only leaves at distance b. Some other subtrees here, they may contain only leaves with distance a. So if you look at all neighbors of C, at all these trees, you must have some trees containing only leaves of distance b, some trees containing only leaves distance a. Yeah. So I need to look at all neighbors of C. For every neighbor, look at all leaves. They all must be on the same distance, and then out of all these distances, I need to check that I can split it in 2 classes. Okay, it's complicated, I know. So it's pretty nice graph problem. So let's see. So how do I implement it? I usually implement trees like this. So this is my normal implementation of trees. So I just have like normal graphs. I have vector of vectors of all the neighboring edges, and here I use DFS. For DFS, I just give the DFS instead of having marks, I give it a vertex and a parent. Yeah? And just I go to all neighbors of x and x except p. So p is my parent. So I visit all neighbors except p here. So d is my distance. Yeah. Okay, so this is pretty default DFS for calculating distances in a tree. Here I will find the diameter. So I find diameter like this. I find the farthest possible node x from 0, and then find the farthest node from x. Yeah. So this is how you find the diameter of the graph. This is the easiest way, I believe. So you start from any node, find the farthest node from here, find the farthest node from here, you have a diameter. Now you need to find the center of this diameter. And I am doing it incorrectly. Let me show you. So this is incorrect code for finding the center of diameter. Can you see why it's not correct? Because I actually spent too much time looking for this. Okay, so I will, okay, spoilers, I will get the wrong answer for this submit, and then I will spend another like 10 minutes just looking for this specific problem. So this code is incorrect. Okay, exercise for you, find why this code is incorrect. What I'm trying to do, I'm trying to find the center of diameter. So here, what my code is doing. So I start from node 0, find the farthest node x. From this node, I find the farthest node y. This part is correct. So this is how you find the diameter. Now I need to find this center of diameter. And I'm doing it like this. It's incorrect. Okay, you may think why it's incorrect while I finish. So now from this center, I need to, okay, this part I will also write incorrectly first. So what I'm doing here, so I call DFS from this node, central node, find all the distances to all the leaves. So this set ds will contain all distances to all leaves. And see if I have more than 2, then it's incorrect. If I have 2, then I will do it like this. Okay, so this part is boring, this part is boring. Yeah, now I need to find distances to all the leaves. Okay, here's n minus 1. It's not interesting, not interesting. Yes, right now I just put all the distances to the, I need only to put distances to leaves. Yes. I'm just checking that I calculate everything correctly, so I find the correct diameter, find the correct center. No problem here, I thought. Yeah, here I put all distances. You need to only put distances to the leaves. So I will go and add this. Yeah, so here I need to check if I have a leaf. I do it like this. I calculate number of children. If I have 0 children, I have a leaf. Then say that doesn't make sense. I can just check if it is leaf or not. So I will just see. So if I have at least 1 child, then it's not a leaf. Yeah, false. Boring. Yeah. So now I have leaves. Finally this. Okay. Now I have wrong answer for the second example. Actually, good examples. So what's happening in the second example? I just draw the second example. Okay, see what's going on. Okay. So I find diameter from 7 to 4 makes sense, and the center is 5. And from this 5, you see, you have 2 different distances. From this center 5, you have leaves on distance 2. This 2 and 7, they have distance 2. And 4 have distance 3. So you have only 2 different distances. Yeah. Okay. So that's when I understand that it's actually yeah, it's a little bit more complicated. So I need to check for all neighbors of C if in every subtree I have only leaves with the same distance. Okay, so I need to update my DFS once again. Yes. So again, I look at all neighbors of C, call the DFS, and in this DFS I need to find distances to all the children, to all the leaves. Okay. I will rewrite this program once again. So I will do it like this. I will maintain set of all distances to all leaves. Yes, since I already use DS, this will be called DDS by perfect naming conventions. So here, I said I don't need this array leaf. Okay, so I don't need this. No. Yeah. So here I will take the set DDS, clear it first, then call DFS. DFS will find all the leaves and put all the distances to all the leaves in this set DDS. Then in the end, I will check if I have more than one distance, then it's already incorrect. If I have only single distance, I put it to array DS. Yes. So now in the end I will check if I have the final part is the same. No, that's it. So now I will submit it, and then for the long, okay, I get a wrong answer, test 10, and then I spend a lot of time just thinking why I have wrong answer test 10. Sometimes it happens, sometimes your bug is not that obvious. So again, I read the problem statement multiple times. I read all my functions. I read function DFS. I call DFS, it looks kind of suspicious. So I read it multiple times, but it looks fine. So what I'm doing here, this leaf is Boolean, which checks that current node is leaf. If I have at least one child, it's not a leaf. If it is leaf, I put this. So it looks okayish. Yeah, so it's not the best code in the world, but it should work. Yeah, so here I check, I find the diameter good. Here I still don't understand what's happening here. Here I think I divide by 2. If the diameter is odd, is it true that I can pick any middle position? It looks to me that yes, but then I decide to check. Okay, so I thought okay, if I have something like this, so I have one length is 0, so I have this in the middle of diameter. Then I said okay, it's not diameter. Yeah, so diameter is 4. So here diameter will be even. So to make the diameter odd, I need to do something like this. Yeah. So this is how you make the odd diameter. But in this case, you can pick any point in the middle. Yeah. So this part should work. Okay, then I spent too much time. Too much time. Pum, pum, pum. Okay, then I decided to prove myself once again that I'm correct. So again, I'm drawing the same picture and just proving myself that my solution is actually correct. Yeah, it's nice nice exercise actually. When you think your solution is correct, but you have wrong answer, just prove yourself the solution is correct. Yeah, like if it's not your solution. So if you want to prove someone else that your solution is correct, and I'm proving myself my solution is correct, and it's actually I convinced myself solution is correct. Yeah. Um, so here I think once again, if it's true that I need to pick the center of diameter, and it looks correct. Yeah. So I thought about some corner cases, and all corner cases should work. Yeah. So the center of diameter is actually the correct point to start with. Okay, and here finally, I look at this picture and said, okay, this is actually not looking for center of diameter. Okay, so if you already found this bug, so this code is not looking for the center of diameter. It's looking for the point with the same distance at the center of diameter. Yeah. So for example, here, let me show you. Let me show you. So if I have another point here, which have the same distance at the center of diameter, I can pick this point instead. Yeah. So instead of picking the center of diameter, I picked another point, this point. This point is not center of diameter, but it has the same distance as I need. So I only check distance from node X, yeah, because this array D contains distance from node X. The correct way to check center of diameter, you need to check that this distance is correct and this distance is correct. Yeah, so that's what I will do. So I will calculate distances from node X and distance from node Y. Here I copy array D to array dx. So now I have distance from both x and y. And here I check. Okay, I do it like this. I check that sum of distances is dd. It just means that my node belongs to diameter. Yeah, so sum of these distances equal to diameter. It just means the point belongs to diameter and the distance like this. So that's it. So that's my another mistake. So I made how many mistakes? Like 4 mistakes in this code. Too much. No, that's kind of tricky contest, I would say. So it happens. So that's it. That's problem H. Let's check some of your solutions. Maybe you have easier solution for G. No. Oh, interesting. So you simulate. Okay, so instead of calculating, you just simulate. Why not? Why not? So again, the constraints are small, so so my solution just calculate number of rounds, but here you simulate the operation and see okay, return 1 or 0. So just return if it is if you win or not. And you make a binary search. Oh, that's interesting. That's interesting. That's nice approach actually. I would say it's maybe more general. Oh, good. So again, we can track we can check both. We can check 2 parameters and we don't know the third parameter. So we can do binary search over the third parameter. Why not? Why not? And then just simulate. Yeah, this may be it may be easier solution than mine. Nice. Ooh. Yeah, this one looks similar to mine. So almost there. It's kind of the same. Calculate this, calculate the rounds, and calculate damage, and see if damage is great. But then you need this. That's what you can do. Ah, no, you check how much XP do you buy. Ah, why? Ah, okay. That's another way to doing it. So you know how much money you can spend. Okay, so if I'm buying enough defense point, I will have no damage. Okay. So instead of doing this, you can buy some HP points. It does make sense. You can buy either defense points or HP points. They kind of replaceable, yeah. So you see how much you can spend have no damage, and instead you can instead of buying this defense point, you can spend this money buying HP points. Yeah. So you see this number, and you see, okay, you don't have to buy more HP point if you spend more than this. Yeah. Nice problem. A lot of different approaches actually. Good. What about the last problem? Interesting. Looks different from mine. So what we're doing here? Building the graph. Boom. So look at all. You go from other direction. So you look at all leaves of the graph, and then just I think you will remove them one by one, right? Hmm. Interesting. What does what mean? This one. Here, this lambda function. So we have instead of making a special function, you can declare the function inside the code. So this is just function which takes two numbers and returns nothing, and it does the following. So it takes two numbers u and v, take the what is v vector psi. What's psi? Pairs cc, pair of two sets. Okay. Okay. So we have vector of pair of two sets. Sometimes I love C++. Okay. So we take the first of them and erase. I think you erasing the edge from your tree. Okay, and you do it by maintaining the sets. So you need to erase this element from this set and this element from that set. Okay, it looks kind of strange, but it should work, yes. I'm not sure what you're doing here, actually. So we have the queue, yeah? That's up here, yeah, that's queue. We push all elements in the queue in some arbitrary order. So put all the leaves in the queue, then take the, if it is not alive, continue. Okay. First, second size. It's very tricky what's happening here. So I think we just cut all the leaves until until we meet the kind of junction points. We have when you have some middle node which is not which has more than more than one child. So we can see if it has two leaves attached, we can combine them into one. Okay. It's very interesting code stuff. Nice, interesting solution. So again, so my solution finds the center and then start from this center outside. You starting from leaves and going back to the center. So I think it will eventually does the same thing as mine, but it's completely different approach here. Nice. Okay, so for today. See you next week. Thank you.